Hi, my name is McKenna, and I worked with Miles and Owen on our project called Urbanization Hydrology. Our project aims to quantify the effects of urbanization on the hydrology of Monument Creek. To do this, we measured the meander and sinuosity, the discharge, the sediment flux, the slope, the velocity, and the characteristics of two cross sections. One of these sample sites was before Monument Creek is reinforced by concrete, and the other sample site is after. Our guiding research questions were: how does the change from natural banks and meander to concrete banks and forced meander affect Monument Creek and its associated floodplain? And how likely is our channel to reach the first floodplain, and how likely is it that the whole floodplain will fill? The location that we visited, we took two sample sites from Monument Creek with different creek characters. Our upstream sample site is located just upstream of the U.S. Geological Survey's gauge that we used to collect some of our data. This sample site has a greater meander and is located before Monument Creek is reinforced by concrete. Our downstream sample site is located just south of the Woodman Road Bridge, and this sample site has less meander and is reinforced by concrete. Both of our sample sites are located after Monument Creek's convergence with Pine Creek. In collecting samples and our data, we used Google Maps to produce a value for sinuosity for Monument Creek by dividing the bank length by the length of the creek as the crow flies. We also used Google Maps to take elevation values to calculate the slope across each segment. We then used data collected by the U.S. Geological Survey's gauge located at Monument Creek at Woodman Road to produce a discharge value for Monument Creek. We also used a flux sampler to take two sediment samples in the thalweg at each site. This is the area of the creek that is the deepest, in a 1 minute period of time, and brought them back to be weighed. We also used a velocity meter to take 3 velocity measurements in the thalweg at each site and calculated the average velocity. We also used laser surveying equipment to take elevation measurements to conduct a cross-sectional analysis of two cross-sections. Again, one of our samples is before the creek is reinforced by concrete, and the other one comes after. Lastly, we made note of the creek bed characteristics that we then used to calculate Manning's number, which is a friction coefficient. Starting into our analytical methods and results section, first for discharge, we used data collected by the U.S. Geological Survey's gauge located at Monument Creek at Woodman Road, and on April 11th, this discharge value was 30 cubic feet per second. Next, for sinuosity, we divided the bank length by the length of the creek as the crow flies. So for Site 1, which is our upstream location, the sinuosity measurement is 1.57, and for Site 2, our sinuosity measurement is 1.07. We expect these data because they reflect human modifications to Monument Creek straightening the meander.
Measuring the fluxes of a creek can be a good indicator of how erosive they are. We measured the flux of Site 1 to be approximately 19.1 kilograms per cubic foot per minute, and for Site 2 to be approximately 61.6 kilograms per cubic foot per minute. At each site, we divided the elevation change across the segment by the length of it to produce the slope. At Site 1, the slope was approximately 0.00739, and at Site 2, it was approximately 0.0132. Using velocity meters, we measured the velocities of the two sites to be approximately 2.3 feet per second for Site 1 and 2.421 feet per second for Site 2. We believe the measurement for Site 2 is flawed because it should be a significant increase from Site 1 due to the fluxes. We'll go more into this when we talk about our calculated velocities. Now we get into the cross-sectional analyses. We took two cross-sections, one for Site 1 and one for Site 2, and we did some calculations for both. We calculated the cross-sectional area of Site 1 to be approximately 102.713 feet squared when it was at bank full, and approximately 645.303 feet squared when it was at a twice bank full flood. For Site 2, we calculated the cross-sectional area to be about 29.2 square feet for a bank full flood. For a flood that would encompass the walking area up above the creek, we calculated the cross-sectional area to be about 333.9 square feet, and this would be approximately a 10-year flood. We used these cross-sectional areas to calculate the expected velocities for the creek. In addition to the cross-sectional areas, we need the slope, the Manning's number, and the wet perimeter to calculate the expected velocities. The Manning's number is subjective, but we figured it was somewhere around 0.059 for Site 1 when it was unflooded, 1.54 for Site 1 when it was flooded, and 0.03 for Site 2, both when it was flooded and unflooded. Site 1 had a lot of trees and bushes above the banks that would have interfered with flow when it was flooded, whereas Site 2 was mostly concrete above the banks, which would have not interfered with the flow at all and increased the power compared to Site 1. The slopes were the same that I mentioned before, 0.00739 for Site 1 and 0.0132 for Site 2. The wet perimeter was calculated using the average depth and the width. For Site 1, we got approximately 54.428 for it unflooded and 262.814 for it flooded. For Site 2, it was approximately 25.066 unflooded and 116.89 flooded. Using all of these numbers, we can calculate the expected velocity. For Site 1, when it was flooded, we got approximately 1.51. For Site 1, when it was unflooded, we got approximately 3.32 feet per second. For Site 2, when it was flooded, we got approximately 11.49. And when it was unflooded, we got approximately 6.32 feet per second. The reason Site 1 is slower while flooded and Site 2 is faster while flooded is because of what was mentioned earlier with the Manning's number being different because of the increased resistance at Site 1, whereas with Site 2 there was no increased resistance above the banks.
So at these two sites we found the discharge in cubic feet per second, both for when they would be unflooded and flooded. So that's what these numbers are, the unflooded and flooded discharges. There are some issues with these numbers though. For example, the 340.6 seems like a reasonable yearly flood, or even a little more than yearly, but 977 for the whole floodplain flooding seems pretty unlikely. We expect that we increased the Manning's M too high in an attempt to account for the trees and other organic matter that would be in a larger floodplain, and by doing so, underestimated the cubic feet per second that would happen during a flood. For Site 2, you can see how this lower number just means that we had bankfull too low. 184.3 should be comparable to 340.6, but it's low, and that's because we didn't pick the right bankfull height. It was difficult to identify a bankfull height at this site because it was an unnatural creek. It wasn't natural like the first site. This 3,835 seems a lot more likely for a flood. That would be a more rare, more significant event. That seems like a more reasonable number than the 977. Here you can see the peak flow versus the return interval. So that's a lot of what we're basing our data on. This return interval is how many years a flood of this size would occur. So like in that last slide, a 340 cubic feet per second flood could happen with the interval of about 1 year. It could be pretty common. Whereas a 3,800 cubic feet per second flood could be once every 25 or 30 years. It could be a much rarer event. And then we just have a few more things to discuss before we're finished up. Among those is it's important to understand the effects of the erosion potential, the effects on the erosion potential from the human changes to it. So straightening the creek and increasing the velocity increases the power of the creek, which increases its erosional potential. This has led to a huge transport of sediment downstream, much higher than usual, which you can see if you look at the satellite images of the confluence of Monument Creek and the Arkansas River. In certain sections of Monument Creek as well, the erosion has been so significant that the sediment has been completely washed away, and the creek is just running on top of bedrock at this point. The goal of the study was to better understand how changes resulting from urbanization influence the character of the creek, and we can see that it's a pretty significant change. It seems like the only adequate way to reverse the damage that's been done by the concrete barriers is to allow it to meander. These concrete barriers are terrible for the health of the creek, and so allowing meandering with lower velocity, with lower power, and it would encourage more sediment deposition. And even if you can't allow the creek to fully flood and fully be in a natural state, just having less straight concrete barriers and more room for the creek to meander would allow the creek to be healthier. If we were to do this experiment again, there are a few small things we would have changed. Our 2 points were relatively close together, only a few hundred meters apart, and by taking our first site further upstream in a more meandering area and our second point further downstream, fully contained within a controlled area, we could have gotten maybe even more polarizing data. Additionally, our volume measurements were ineffective. It seems like our instruments weren't working correctly, and so we could have used other methods to more confidently get a measure of velocity in addition to what we calculated. Other than this, most of what we saw that we expected. The sections of the creek that were contained in concrete were much less healthy, with higher flow rates, significantly higher sediment load, which just increases erosive capability and has significantly damaged the stream downstream and has also affected its interactions with downstream communities like Pueblo. By allowing the stream to meander, the stream would be healthier, the communities around the stream would be healthier, and the city of Colorado Springs would have to spend less money on projects to control the stream as well. So allowing the stream to meander would be a pretty significant positive.